All right, good morning, good afternoon, everybody. I'm Chris Spinagle from the Warning Decision Training Division. I'd like to welcome you to today's Storm of the Month presentation. Today's presentation comes to you from the National Weather Service office in St. Louis, Missouri. Our presenter is Ben Herzog, who will be presenting giant hail in central Missouri. And with all that being said, Ben, the floor is yours, so go ahead and take it away.
All right, well, thank you so much. Thank you all for having me come on and talk about this topic. I've always found these Storm of the Month talks very fascinating, just a great way to share some science, share some unique storms that move through our forecast area. And I'm really excited that I get to present this pretty interesting case to this audience. It's obviously an interesting case in one respect that we have giant hail. We don't see that all that often in our forecast area, but we do on occasion. And of course, there's some interesting things that go along with that, including, your typical hail signatures. But there are kind of a couple of extra reasons that I think this case is particularly interesting. First of all, we had some false signatures that could pretty easily be confused with those of a tornado. In fact, some of them could be confused with a pretty significant tornado. And so we're going to kind of get into that and see what that looks like. But what's unique about this as well is we've got a pretty unique data set on our hands. So if you're familiar with the radar coverage in our part of the country, central Missouri is a bit of a radar hole. Our lowest radar beam is usually between like 8 and 10,000 feet. So there's an awful lot of air that we're not seeing there. But the University of Missouri's got an X-band radar in Columbia that's able to give us a pretty unique look at some of these storms. And on top of that, the University of Missouri was able to fly a sounding for us about 30 minutes before the storm came through. So really some interesting stuff to look at in here. So with that, we'll go ahead and get started. So before we get going into the data, I just kind of want to set the stage a little bit what we're looking at. This is the 12Z analysis from April 4th, 2023. As you might expect, on a day where we've got some severe weather in the central part of the country, there's a pretty amplified trough over the western CONUS. We've got a couple of short waves marked here, but generally southwesterly flow pushing into my neck of the woods. That star is on top of St. Louis, where our forecast office is at. And you can see that there's a pretty good jet that's starting to kind of round the base and push into the central part of the country. Moving on down to 500 millibars, you can see we've got a closed low moving from Utah into Colorado and Wyoming. Again, a bit of a mid-level jet here pushing from kind of the southwest into Kansas and western Missouri, really providing some pretty ample dynamics for the system. Jumping ahead to 18Z, looking at a surface analysis from WPC, you can see we've got a surface trough extending from kind of the Texas and Oklahoma panhandles up through Kansas, culminating in a surface low in eastern Nebraska with a warm front then extending across southern Iowa and into the Midwest. That puts my forecast area, which is in east central Missouri and western Illinois, solidly within the warm sector. You can see our temperatures at this point are pushing into the 80s and our dew points are mid to upper 60s. Getting a slightly different look at that to maybe make these dew points show up a little bit better here at 18Z. This is the SPC meso analysis. Again, temperatures solidly in the mid-80s, dew points in the low to mid-60s. So that's certainly supportive for some severe storms in my forecast area. Trying to take a bit of a closer look at some of the environmental parameters in my forecast area this day. Here's a look at low and mid-level lapse rates, and they're quite steep. Especially in the northern forecast area, we've got 0 to 3 kilometer lapse rates in excess of 7.5 degrees Celsius per kilometer, and our mid-level lapse rates are especially steep in excess of 8 degrees Celsius per kilometer across the entire forecast area. As you might expect with those steep lapse rates and the temperature and humidity I was showing at the surface, our instability is rather high. Generally 2,500 to 3,000 joules per kilogram of mixed layer CAPE across northern Missouri, and then our most unstable CAPE is between 3,000 and 4,000. On the right-hand side, we've also got effective bulk shear plotted, and you can see that we're easily topping 50 knots across the entire forecast area, getting close to 60 knots in some areas. So certainly, CAPE and shear parameter space is very supportive for severe thunderstorms. Taking a look at something specific to hail, this is a hail growth zone CAPE. So this is your CAPE between -10 and -30 C. And again, around 1,000 joules per kilogram across kind of northern Missouri. That's certainly supportive to see some large hail. And then I've got LCL heights plotted on the right-hand side here. I wanted to show this because when we get these LCL heights above D or 1,500 meters, that starts to become pretty prohibitive to tornado genesis. So everything we've seen right now would stand to reason maybe we could see some tornadoes, but this is kind of the first thing I'm looking at, like, well, maybe that 1,500 meter LCL heights are going to keep those cloud bases just a little bit too high for us to see many tornadoes. And indeed, as we start looking at some more tornado-specific parameters, we can see the effective storm relative felicity is quite low, especially across Missouri. As you get into kind of more central Illinois along the warm front, it does ramp up, but that's getting pretty far outside of our forecast area. And especially as you get towards central Missouri, that effective storm relative felicity and the 0 to 1 kilometer bulk shear are not particularly supportive of tornadoes. So taking all that information in, this is what the SPC convective outlook looked like at the 16Z update on April 4th. You can see my forecast area, which I've kind of crudely drawn there, is straddled by a couple of moderate risks to our north and our south, with an enhanced across most of the St. Louis CWA. You can see those moderates are largely tied to the 15% tornado risks, again, north and south of us, though we do have some hatching in our CWA, so they're at least thinking there could be some potential for some significant tornadoes, 30% wind across the CWA, and then 30% hatched hail in our northern forecast area. And hopefully you can tell by the title of my talk, that's what we're going to be focusing on, is the hail threats. Switching over to some kind of observations of what was happening, this is a visible satellite loop running from 16 to 20 UTC, and you can see we have largely pretty discrete convection, and actually not that much of it either. You can see we have convective initiation over west central Missouri sometime around 17 or 18 Z, and then those storms just push into central Missouri as we get into the early afternoon. Taking a look at what that looked like on radar, this is just the MRMS composite reflectivity from 18 to 20 Z. And again, pretty discrete convection, not very widespread, and really we've just kind of got this one storm on the southern end of this small little complex that's sort of dominating everything that's going on right now. This is where some of the unique data set comes in. The star is just to the southeast of Columbia, Missouri. That's where the University of Missouri was able to fly a weather balloon at 1937 UTC, I believe. So toward the end of this loop, right before the storm kind of moved through the area. And really just, I thought it was a very fascinating piece of data to take a look at. Of course, the one thing that really stands out to me here are the very steep lapse rate. You know, you're nearly dry adiabatic from like 800 millibars up to probably 400 millibars. You obviously do have that small inversion there around 850, and then you're very steep again in the low levels. And so obviously that's quite supportive of hail. What I've got highlighted in that little blue line there, I'm trying to show where the hail growth zone is at between -10 and -30 C. And you can see there's quite a bit of space between the temperature trace and that moist adiabat. And so certainly ample instability in the hail growth zone. This substantiates the large instability that we saw in the meso-analysis. And in fact, if you look, it's probably a little bit hard to see, but I can read off the CAPE values here on this sounding. Our mixed layer CAPE is around 2,700 joules per kilogram. Our mu CAPE's around 3,000 joules per kilogram. So right around the values that the meso-analysis is showing us, giving me some confidence in what we were seeing on there. And then another thing that I note here is that our freezing level, which is marked in this blue little line right here, is not very high above our level of free convection. And so that's telling me we're really not having much in the way of warm rain processes going on. We've got an awful lot going on and as we get above freezing and kind of into the mixed phase region. And so, again, pretty supportive for hail growth. Of course, with that sounding, that comes with a hodograph as well, and there's some interesting features on here that are standing out to me. First thing I noticed is we've got relatively large storm relative inflow. That's just kind of taking a vector from the right-moving storm motion and into sort of the effective inflow layer of the storm. And you can see we're from about 36 knots or so coming into the storm. And so the general idea here is when you've got this large storm relative inflow, you're going to have larger mass flux. So you're just pulling more stuff into the storm. Really, you're pulling more moisture into the storm. And that's important because that's going to result in wider updrafts. And we're going to talk about why wider updrafts are important here in just a moment. The other thing that's apparent to me is there's not a whole lot of curvature on this photograph, and actually that's something that we were looking at in the lead up to this event, kind of questioning how much was there going to be a tornado threat given relatively straight photographs. Well, another feature that's been found about these limited curvature photographs, they also tend to feature wider updrafts, and that's supported by some research that's been done fairly recently. So I keep talking about these wider updrafts. Why is that important? Well, when you've got a wider updraft, you're able to kind of shield the core of the updraft from the detrimental effects that entrainment has on these parcels that are kind of rapidly rising through the storm. If you think about the entrainment coming in, that's actually going to help cool off those parcels. That's going to limit the ascent. But when you got these very wide updrafts, that entrainment having much less of an impact on the core of the updraft, so you're going to get stronger updrafts and you're going to get larger hail. So not only does our sounding here support large hail with those very steep lapse rates, especially in the hail growth zone, but our hodograph is actually giving us some ideas that we may be dealing with some large hail with this environment. So with that in mind, let's go ahead and take a look at the data. And so I'm going to try something a little bit different from what I normally do. I'm actually going to kind of play around in GR. I'm going to try to point to what I'm looking at with my mouse here, and we'll go from there. And so to kind of orient you, I'm going to zoom out real quick to show you where I'm at. Hopefully you can see the outline of Missouri here. You can see this nub in eastern Missouri. That's where St. Louis is. Right in the center here is Boone County. Columbia is one of the larger cities in our forecast area. And then the storm is just to the immediate west of our forecast area. It's about to move out of the Pleasant Hill CWA into the St. Louis CWA. I'm going to zoom in on this storm a little bit more and orient you with what we're looking at. We're at the half-degree tilt. In the top left, I've got reflectivity. In the top right, I've got storm relative velocity. In the bottom left, I've got correlation coefficient. And in the bottom right, I've got spectrum width. And so kind of diving in here, one of the very first things that is standing out to me is this area of enhanced inbound velocity, right kind of where what looks like a hook on this storm might be. And so, you know, we've got the inbounds to the south, we've got the outbounds to the north. Well, that could be some cyclonic rotation, and there are kind of higher values there on some of those higher velocities as well. So it's got my attention, but when I see features like this, really when I see any features in radar that have me thinking, oh, maybe this is a tornado, maybe it's a hail core, maybe it's whatever, I first kind of try to examine the data a little bit more thoroughly and try to figure out how trustworthy it is. And so I'm going to put this red box right in the middle of where some of those higher velocities are at, and I'm just going to see what some of these other radar moments look like. Over on reflectivity, you can see we're relatively low in that area, between 20, 25 dBz, so it's not so low that I can conclude that it's non-meteorological or maybe some sort of radar artifact, but it's at least got me scratching my head. If we were more like 30, 40, 50 dBz, I'd be more willing to believe that, but I'm already kind of questioning it. You look down in the bottom right at spectrum width, and we notice, oh, well, spectrum width is pretty wide here as well. So maybe there is some sort of radar fact going on, or radar artifact that's showing up here. Another thing that I try to do to kind of suss out whether or not what I'm looking at is real is try to find some temporal and spatial continuity in this feature. So I'm going to step back a few steps, and then I'm going to step forward. I'm going to step back, and I'm going to step forward. Something about those higher velocities just doesn't really seem right. They kind of start out well ahead of this storm, and then they seem like maybe something's getting sucked into the storm. I'm not really sure what's going on there. But again, it's just not seeming quite right to me. And then as we tilt up from the half-degree tilt to 0.9, well, we definitely have got very high velocities at 0.9. And then we go to 1.3, and that same feature is there. And actually, as you look here, we're associated with much higher reflectivity. So I'm thinking that this signature is a little bit more trustworthy higher up the deck, where we've got these higher inbounds associated with the higher reflectivity. And so taking all these things in, noticing what's going on aloft, my immediate thought is we're looking at some side lobe contamination going on in the bottom tilt here. So I'm guessing most of you have probably heard of side lobe contamination, but to kind of help you remember what that is, I want to just cover that real quick. And so here's kind of a schematic of a radar dish, and we've got the main beam coming out. That's that huge kind of oval in the middle there, and that's where the vast majority of the energy a radar beam is going to be going out. But due to just kind of how radar dishes are engineered, we're always going to have side lobes. This graphic makes it seem like they're only in 2 dimensions, but actually these side lobes are going all the way around this main beam. And whatever little energy is reflected back from these side lobes, our radar processing software is going to plot it where it thinks the main beam is at. So to kind of illustrate that a little bit more, here's a cross-section of our storm. It's looking from the south, so you can see west is on the left, east is on the right. And then here's the radar in St. Louis, way to the east of the storm. Here's the main beam going out, and the vast majority of the energy from this beam is going to be in this area, and it's going to get the right information. However, we're going to have these side lobes. They're getting skinnier because they're less energy. These are not to scale. I think this would have to be much, much skinnier relative to the main beam to really illustrate how little energy is in here. But nevertheless, there is some energy in these side lobes. And if we flip over to velocity, see where these really high values are at, and then we compare that to reflectivity, there's kind of something interesting that stands out to me. As you get immediately above these range gates, these side lobes are interacting with increasingly high reflectivity. And so that high reflectivity is going to be able to, in some ways, kind of overpower, I guess, for lack of a better word, the reflectivity in the lowest tilt. And so whatever velocities are associated with these higher reflectivities aloft are going to end up being plotted down here on the bottom. And I think that's what we're dealing with here. So, there probably is some rotation in this storm, but I don't think the rotation in the lowest levels that we're able to see is entirely accurate. So that's kind of the first unique radar feature that we're looking at. I'm going to switch back over to the radar, and we're going to go forward a little bit and just kind of see what other interesting things crop up as we move forward in time. So we're going to go about 5 minutes ahead of time, another 5 minutes. So now we're at 2019 UTC. And there, again, some interesting features going on here. Hopefully one that really stands out is the presence of our three-body scatter spike coming out of the back of the storm. You can see that here in reflectivity very clearly, and it really shows up nicely in correlation coefficient as well, where we've got those very low CCs coming out the back of the storm. Certainly an indicator that we've got some hail in the storm. We can't really glean a lot of information about exactly how large that hail is. I think maybe with the environment we can be confident that it's going to be putting down some larger hail, but certainly hail going on in that storm. Another thing that I'm starting to notice is we're getting kind of these lower echoes starting to get bounded by higher echoes. So we've got some evidence of a weak echo region. And as we tilt up from 0.5 to 0.8 to 1.3, definitely some signs of a bounded weak echo region in here. Definitely some signs of pretty strong rotation in the middle portion of this storm as well. So again, not a lot of information directly about hail, but certainly some evidence that we've got a pretty strong updraft going on in this storm. As the storm is getting ready to cross into our forecast area, we think that these higher velocities in the lower levels are probably inflated due to the sidelobe contamination. And we also are thinking the environment's not particularly favorable for tornadoes, but it is for hail. And so right about now, if we don't have one out, we're issuing a severe thunderstorm warning. Gave some thought to a tornado warning because of those higher inbounds, but we're thinking that's an artifact. So we're doing severe thunderstorm warning at this time. Let's step forward a few more and get to here at 2029 UTC. Those inbounds have all but gone away, much weaker rotation in the storm. But in that same portion of the storm, all of a sudden there's something very fascinating that shows up on correlation coefficient, where we've got these really low values in there. That's kind of on the hook of the storm. It's not exactly where I'd expect it to be, but at first glance, I feel like that could pretty easily be confused for a tornadic debris signature. And then, I mentioned earlier, I like to look for continuity in these features spatially. And so let's see what that looks like. We go up. Oh, that's still there. We go up. It's still there. It's still there. We're upwards of, almost 30,000 feet now, and it's still there. So that's kind of a concerning signature to me. And so what I want to do is take a cross section and see what that looks like. Let me pull this over here and turn on correlation coefficient. And lo and behold, whatever this feature is, it's going from as low as the radar can see, somewhere around probably 8,000 feet, to nearly 30,000 feet. And it just kind of has the appearance of what some of these really big TDSs look like. And so previously we were thinking about, well, do we need a tornado warning? No, it's probably some bad data in there. And all of a sudden we see this feature too that looks, kind of tornado-y. And so we're like, palms are sweating at this point, because if this is a tornado, I think this is probably a pretty big tornado if we're getting to 30,000 feet. So let me switch back over to my slideshow and kind of talk about this nomogram that we help use to kind of estimate tornado strength. And so on the left-hand side, we've got TDS height. On the bottom, we've got maximum rotational velocity. And if we take that TDS height of 30,000 feet, that is putting us solidly in the EF4 plus category. And so that's really concerning for what we're seeing. However, I mentioned the rotational velocity is pretty low. I think this 25 knots that I've even got shown on here is probably pretty generous for what was going on the radar. But you can see where these two lines cross. That's completely outside of the data set of this study. So that's just another kind of knock on whatever we're looking at here. Something just isn't entirely making a lot of sense. So is this a TDS? Probably not. Moreover, as we mentioned, we've got very high LCLs. That's very likely prohibitive to tornadogenesis. And then the STP is really low. We would expect to see much higher STP for a TDS of that magnitude. So again, that just kind of illustrates the idea that given this environment, we're not really expecting tornadoes. We're certainly not really expecting these significantly severe tornadoes. So if it's not a TDS, then well, what the heck are we looking at? I've pulled up this kind of CC chart, showing typical values of CC and highlighted the range in which those low correlation coefficient values were. I actually probably could have extended this further to the left because some of those CC values got very, very low. Because of that, I'm thinking it's highly likely we've got some non-meteorological echoes in there, be it biological targets, maybe some chaff, I'm not sure. But as we get to kind of the higher end of what we're looking at in this kind of bin, we do see a couple of things in there. Well, snow would be one option. It's probably not much snow, given that we've got, deep convection ongoing, but could be looking at some giant hail in here. And so that's definitely something that's got our attention, especially given the environment that we're dealing with right now. I'm going to switch back to the radar. I'm going to turn on some differential reflectivity down here. And the other thing that we notice is the differential reflectivity is really quite low, really throughout the depth of the storm. When we get these really low differential reflectivities, that's telling us, as we get towards zero, we're looking at kind of more spherical type of hydrometeors, or at least hydrometeors that appear spherical to the radar. And that can be another signature of large hail. And actually, one thing I completely forgot to look at was really excited to show you was what some of these lower CC values look like on the Columbia radar. So let me switch over to that. This is the Mizzou radar. It's an X-band radar, and so it's quite a bit more limited in how far it can see. And there are a few data artifacts, and I'm not entirely sure what to make of them. Like this velocity is pretty messy, and the differential reflectivity that I've got down here isn't quite what I expect to see. But we've got a lot of good information here for the reflectivity and the correlation coefficient. I'm going to come down. This is the 0.9 degree tilt. That's the lowest tilt available on the Mizzou radar. And you can see this lowest tilt looks a lot different than the one we saw from the St. Louis radar. There's actually much lower correlation coefficient on kind of the northwestern flank of the storm. And then as you get into where the higher reflectivities are at, correlation coefficient is a little bit more representative of what you'd expect to see in that part of the storm. As we tilt up, the lower correlation coefficient remains on the northern parts of the storm. And eventually, as we get up to about 6.5 degrees, now we're looking at a similar height to what we could see from the St. Louis radar. And those are those very low correlation coefficient values that are finally showing up in there. That kind of looks like what we saw in St. Louis. So to take a cross-section of this part of the storm, this is going to be a little bit messy, but hopefully we can kind of see what we're trying to find here. So again, we're looking from the south to the north, or kind of the southeast to the northwest. These lower correlation coefficient values are extending actually from the northern part of the storm, kind of tilting to the south more or less. And that's, again, just not what we would expect a TDS to look like. And so that's kind of further evidence that very likely not dealing with tornado or anything here, but more likely some sort of biological targets and perhaps some very large hail. Flipping back over to my slides over here, we do the same thing with typical values of ZDR. We're somewhere here between about -1 and 0. And, looking at what's in here, so clutter, anomalous propagation, ice crystals, probably not snow, maybe some graupel. But again, this large hail is certainly very much in play here. And you couple that with what we were seeing with the correlation coefficient, and I'm thinking it's pretty likely we're probably dealing with some large hail. And wouldn't you believe it, here's what some of the hailstones look like as that storm moved through northern Boone County. We had a couple of reports of baseball-sized hail, plenty of tennis ball-sized reports, lots of very large hail. And this is actually kind of the third event that came through that portion of the CWA, actually that county, in a span of about 2 weeks that gave us some of this really large hail. So with that, I'm going to go ahead and wrap up. If I had to kind of summarize the points I had here is certainly try to remain as aware as possible as radar artifacts, those sidelobe contaminations. Really interrogate some things, immediately might look like, oh gosh, that's a tornadic debris signature, but that doesn't quite make sense with what my conceptual model of what's going on right now. Explore that, try to figure out, a little bit more information about that, and then lean on your expertise when making these warning decisions. Use those conceptual models to kind of help you make the best decision you can. And then if I had to guess, that CC dropout that we're looking at is probably some sort of biological target, but to be honest with you, I'm not really sure what that is. So, I'd be really fascinated to hear if any of you got some thoughts about what we might be looking at there. So with that, I'm going to go ahead and wrap up. I'd be happy to take any questions.
All right, I think we're going to wrap it up then. If you have any questions, I'm sure you're welcome to reach out to Ben at any point. And Ben, thanks for your time today.
Yeah, thank you all, and I hope you all enjoyed it.
All right. Enjoy the rest of your day, everybody. Thanks for your time, and we'll talk to you soon. Have a good day.